Today we're going to begin talking about limits. Limits are one of the central ideas that allows us to do calculus. Mathematicians, a general pattern of mathematics is mathematicians try to fill in holes in structures by making new definitions. So what I mean by that is equations like x plus 3 equals 0, for a while that didn't really make sense. So mathematicians had to come up with a new type of number in order to describe this, saying, okay, now we're going to have negative numbers. If you think about in terms of the physical world, when it was an agricultural society, it didn't really mean anything to have a negative number. But in order to fill this problem that, hey, we want this equation to have a solution, they created a new type of number, a negative number. Or here, much more recently, well, does this equation have a solution? When we talked about it in Algebra 1, we said, no, it doesn't. There's no real number multiplied by itself, but mathematicians created a new set of numbers, the complex numbers, that would be solutions to this, so plus or minus I. They create new number categories. And limits arose from this idea, trying to not necessarily create a new number, but to fill holes in a structure. And limits are the attempt of mathematicians to describe where a function should be. So here's an example of a function that has a hole at 3, 2. So it's mostly linear, except it has a break. But what we would say is that it is true that the limit as x approaches 3, so this is a lowercase lim. I write in cursive for this, just like sine, cosine, tangent, of the function, the limit as x goes to 3 of the function, so as x approaches 3, the y-coordinate approaches 2. That is what we would say here. Now, we're not saying that f of 3 equals 2. F of 3 is not equal to 2 in this diagram. But we're saying that as we move the x-coordinates closer and closer to 3, the y-coordinates move closer and closer to 2. The formal definition I'm going to put on a screen in a moment. You don't need to write this down, and I'm not going to be testing you on it, but this is the formal definition. The limit of f of x as x approaches a is c, written limit as x approaches a of f of x is c, if and only if, for all epsilon, this is just a Greek letter, greater than 0, there exists a delta, another Greek letter, greater than 0, such that for all x minus a, the absolute value of x minus a is less than delta, then the absolute value of f of x minus c is less than epsilon. What does that actually mean? Well, it means that if we have a point a comma c, that all the points of the function, no matter how far we look up and down, there's a way we can look left and right so that it's going to come through the left and the right sides of that. So in simpler English, if you zoom on the point b comma c, no matter what way you zoom in vertically, you can zoom in horizontally so that the graph leaves the left and the right sides of the screen. So here's a claim that I'm making, and I'll show you this on a graph. So here's a function. It's not easy to tell that this has a hole, but it does have a hole at the point 1. And see, when I make a equal to 1, there's no actual point because we have x minus 1 in the numerator and in the denominator. But if I zoom in there, f of 1 is not equal to negative 2, but if I zoom in here, no matter how far I zoom in, it gets closer and closer. All the points clearly show that we should be getting closer and closer. There's 1.0 comma negative 1.99996. As we get closer and closer, no matter how far we zoom in, it gets us closer and closer to 1 comma negative 2. So that's what a limit means. In even simpler English, the limit of a function at a point is where the nearby points suggest it should go. Based on these, we suggest that it goes here and here, so that's what the limit is. To evaluate a limit from a table, we'll choose inputs near but not equal to a. evaluate the function at those inputs, and then determine the value that the outputs approach. So for example, if I have this function, I'm evaluating this as x approaches 0. So I'm going to choose points that are really close to 0, x coordinates that are really close to 0. I chose points, some that are slightly below 0, some that are slightly above 0. And when I plug those in, these are the values that I get out. So I plugged these numbers in for x. And if I follow this pattern, okay, this is getting closer and closer, this is getting less and less negative, and these are getting less and less positive. So right in between those should be 0. So that's the limit. Here, as x approaches 4, that means that I want to plug, if I just plugged in 4, I would get out 0 over 0, and that doesn't mean anything. But if I want to look at points near, and this is really important, near but not equal to a. So I'm going to look at points where I'm not actually going to plug in 4. I'm plugging in nearby points and seeing what I get out. So when I plug in those nearby points, I get negative 6.9, negative 6.99, 7, negative 7.01, negative 7.1. So what's the natural thing that these are approaching and that these are approaching? Well, if we look at what's naturally between these, what would we expect to go between these? We would expect negative 7 to be between these. So this is the idea of a limit, that we look at the points really nearby, really close to it, and see where it would get close to. And that's what a limit should represent. Thank you.